This presentation is part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. And for those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. So next I'm going to be talking about objects, types, and values in the language. The basic types provided by the language are sometimes referred to as the fundamental types in the language. And we have a number of different fundamental types. The simplest is the Boolean type, which is denoted by bool, which is just a true or false value. It basically can have one of two values. We have a number of different character types that are, of course, used to represent characters. We have char, which is probably the most common one. This may be a signed or unsigned character type. And then we have signed characters, unsigned characters, and then a few other character types which are typically using a larger number of bits to represent, so they're larger types. You have char 16t, char 32t, and w char t. These are used to represent character types where you might need a very large character set, for example, kanji, like in Japanese, or Chinese character sets where you may have like thousands of different symbols. The character type char is distinct from signed char and unsigned char. This is important to keep in mind. So char, signed char, and unsigned char are all distinct types in the language. There's also a number of integer types, signed integer types. So by signed, they can represent positive or negative values. We have signed char, signed short int, signed long int, and signed long int. And these are listed in order of increasing size in terms of the number of bits that they use to represent values. And then we have a number of standard unsigned integer types, which are unsigned char, unsigned short int, unsigned long int, and unsigned long int. And again, they're listed here in order of increasing size and increasing range of values that they can represent. Continuing on with some comments about the fundamental types in the language, it's worthwhile to point out that some of the type names for character types and integer types can be kind of long. For example, you have unsigned int, or you might have unsigned short int, for example. And a lot of these type names can be abbreviated. For example, int can often be omitted from the names of integer types. So for example, if you just write unsigned, this is equivalent to unsigned int. In other words, you can leave out the int part in the type name. Similarly, if you just write signed is equivalent to signed int. In other words, if you leave out the int, it's implied or implicit in the type name. Also, you can often get away with leaving out signed. If it's omitted, it's just understood. So for example, if you write just int, this is equivalent to writing signed int. So in other words, you can just drop out the word signed. The Boolean character and integer types are collectively called integral types. So if you hear the term integral type, which will show up probably quite a few times throughout these lecture slides, it's referring to one of these three fundamental types. The language also has what are called floating point types, which are used typically to represent real numbers. And there's three types, one called float, one called double, and one called long double. And these are in order of increasing dynamic range that these values or these types can represent. So double, for example, can represent a wider range of values than float, and long double can represent a wider range of values than double. The language also has a type called void, which is essentially a placeholder for nothing. And this is used, for example, when you're specifying return values of functions in the language. Rather than just not specifying anything in the case that the function doesn't return a value, you specify that its return type is void, meaning that it doesn't return anything. So void is kind of a special type that sort of means nothing. It's a placeholder for nothing. And then there's a type called nullputter underscore t, which is a special type that is associated with null pointers, and we'll talk more about pointers later. The next basic concept in the language that I need to introduce is that of a literal, or equivalently a literal constant. And a literal is just an example of a constant in the language, but it's a constant because it literally is what it is. So for example, 123 is an example of an integer literal, and it has the value 123, and it has the value 123 because it couldn't be anything other than 123 because it literally is the value 123. And we have a few other literals here. This is an example of a string literal and an example of a double literal, 3.1415. for example. These are all examples of literals. A character literal consists of an optional prefix followed by one or more characters enclosed in single quotes. So there's some examples of character literals at the bottom of the slide. For example, single quote A, single quote is an example of a character literal corresponding to the character lowercase a. Some of these character literal examples also have a prefix in front of them, like there's a U appearing in front of the single quoted character, and here's a capital U in front of the single quoted character. And the prefix influences the particular type that's associated with the character, type in the language. So if there's no prefix, and this is the most common case, probably for most code that's written, there's no prefix used, in which case the type associated with the character literal is just char. In other words, it has type char. You can also use other prefixes as well to get a variety of other types associated with the character literals. For example, char 16, char 32, and w char t. Again, these are used typically if you're using large character sets, like maybe what's used in the Chinese language or Japanese, for example, that have a very large number of symbols. There's some special characters that are represented by what's called an escape sequence. Escape sequences are character sequences that start with a single backslash. So you have a backslash followed by an N. This is an abbreviation for a new line character, and there's various other special characters that can be represented using escape sequences like what's shown in these tables here. Just a few additional comments about character literals in terms of some of the guarantees that are made by the language. So it's guaranteed in the language that the decimal digit characters are consecutive in terms of their numerical values. So for example, if you take the character 0 and you add 1 to it, this is guaranteed to be equal to the value of the character 1. So in other words, the decimal digit characters are sequential in terms of their numerical values. However, alphabetic characters don't have this guarantee. In other words, if you take the character A and you add 1 to it, this is not necessarily equal to the value of the character B. So you need to be careful when you're writing code not to make assumptions about the ordering of the alphabetic characters. Next, I'm going to talk about string literals. So a string is just a sequence of characters, and string literals consist of an optional prefix followed by 0 or more characters enclosed in double quotes, and each string literal has a character array type. So the type in the language of a string literal, it's basically deemed to be an array of characters. And the specific type of a string literal is determined by whatever prefix or lack thereof of a prefix is used for the string literal. So for example, you can use a prefix of U8, U, capital U, or capital L, and these affect the type in the language of the string literal. Most commonly, people use no prefix at all, in which case it's just an array of characters, array of char. So for example, these string literals here are all just arrays of char, because there's no prefix in front of the double quote indicating otherwise. Adjacent string literals in the language are concatenated. So for example, if you write HEL in double quotes, and then after that you write in double quotes LO, this will be treated as the string HELLO. In other words, these two strings will be concatenated into a single string and treated as such. String literals are implicitly terminated by a null character. So for example, when you write the character string HI in double quotes, what is actually stored in memory, and this character array that's actually associated with this string literal is the character H in capital letters, followed by lowercase letter I, followed by a null character, which is denoted by \0. So a string literal that has 2 characters appearing in it actually has length 3 characters, because there's always a terminating null character at the end. In C++, integer literals can be specified in a variety of number bases, including decimal, in other words base 10, binary, which is base 2, hexadecimal, base 16, and octal, which is base 8. And the particular number base that's used is indicated by a prefix or a lack of any prefix being present on the actual integer literal. So for example, if there's no prefix, this corresponds to a number in base 10, in other words a decimal number. So in the example at the bottom of the slide, 42, there's no special prefix in front of it, there's no leading 0. This is therefore a number which is interpreted in base 10. So it's 42 in number base 10, the decimal number system. You can also put a leading 0 on a number, in which case the number will be interpreted in octal. So if instead of 42, this was the digit 0 followed by the digit 4 followed by the digit 2, this would be interpreted as an octal number, in other words, a number in base 8. You can also put a 0 followed by an uppercase or lowercase b to denote binary, and 0 followed by an uppercase or lowercase x to denote hexadecimal. So for example, at the bottom of the slide here, the 0xDEADU, this corresponds to an integer literal in base 16. The DEAD are digits of the number in hexadecimal. You can also put suffixes at the end of the literal, which can be either upper or lowercase u or upper or lowercase l, or both upper or lowercase u and upper or lowercase l, or LL or capital L, or both u or LL or LL. And these different suffixes denote the particular type of the integer literal. If you want to control whether it's, for example, a long constant or an unsigned long constant and so on. And these are explained in a little bit more detail on the next slide. You can also use a single quote as a digit separator. So if you want to write the number, for example, 1 million, if you want to make it a little bit more clear how the different parts of the number split apart, like the way we would normally write a number with commas, for example, 1 million, we might write 1 followed by a comma, followed by 3 zeros, followed by a comma, followed by 3 zeros. In C++, you can use a single quote character to achieve this sort of functionality for separating digits. You can't use a comma, however, like we might normally write numbers in handwriting. At this point, I'd like to explain in more detail how it is that the type of an integer literal is determined. And basically, there's two key factors: the suffix on the integer literal, which might possibly be no suffix at all, and whether the literal is a decimal literal, in other words, if it's in base 10, or whether it's a non-decimal literal, in other words, in binary, octal, or hexadecimal. So just as an example, I'm going to back up to the previous slide for a moment, and suppose that we have an integer literal 1 million, which is basically this integer literal here. What's key to know here is there's no leading 0 on this literal, so this is a base 10 literal, in other words, it's in decimal, and there's no suffix. So what I'm going to do is consider the kind of the thought process that's involved in terms of what the compiler goes through to determine what the type is of this literal. So in this case that we're considering, there's no suffix, and it's a decimal literal. So we're interested in this particular entry in the table. And essentially what we do is we go through each of the types that's listed here in order, in the order that they're listed, and ask for each of these types, can the particular number that we have, the integer literal that we have, can it be represented with this particular type? So first we ask, can the value 1 million be represented with the type int? In other words, is the range of int sufficiently large that it can represent the value 1 million? If the answer is yes, then the type of that integer literal 1 million will be int. If the answer is no, then it proceeds on to the next type in this list and asks the question, can the value 1 million be represented as a long int? In other words, is the range of long int sufficiently large that it can represent the value 1 million? If the answer is yes, then the type of that literal will be long int. Otherwise, we proceed to the last entry in this list, which is long int, and we ask the question, can a long int represent the value 1 million? In other words, is the range of long int sufficiently large that it can represent the value of 1 million? If the answer is yes, the type of that literal will then be long int. If the answer is no, well, we've run out of types here, which means that essentially what we have is a situation where the literal is so large that it can't be represented by any of the integer types supported by the compiler, in which case we have a problem. And essentially it means you're using too large of a literal. But in practice, this is usually not encountered very frequently. The case of floating point literals is somewhat simpler than the case of integer literals. In the case of floating point literals, the type of the literal is indicated by whatever suffix is used on the literal, or there might not be any suffix at all. So for example, if there's no suffix at all on the literal, then the floating point literal has type double. So for example, if we write a number like minus 1.5 and there's no suffix, there's no upper or lowercase f here, or upper or lowercase l here after the digit 5, this has type double. Similarly, 1.414 has type double. 1.25 e minus 8 has type double because there's no suffix here. The e minus 8 just means times 10 to the minus 8. So this number here is 1.25 times 10 to the minus 8. The minus 8 is the exponent that goes with the base of 10. If we have a suffix of lowercase f or uppercase f, the type is float. The literal has type float. So these are examples of float literals, minus 1.5f. The f suffix denotes it's a float type literal. Here we have a capital F, which means the same thing as a lowercase f. This is also a float literal. And then we have some examples of long double literals at the bottom. If you have a lowercase l or an uppercase L as a suffix, then the type of the floating point literal is long double. So minus 1.5 followed by a capital L is an example of a long double literal. And 1.25 e minus 20L is also a long double literal. This would correspond to the value 1.25 times 10 to the minus 20. Lastly, we have a few other types of literals in the language. The first are some literals that relate to the type bool, the Boolean type in the language. Boolean values can be either true or false. Basically, they represent one of two possible states. And there's two literals in the language, true, which corresponds to the value true, and false, which corresponds to the value false. There's also a literal called null putter, which is associated with pointers, and we'll talk about pointers later, but null pointer or null putter is basically a literal which corresponds to a special value that a pointer can have that denotes that it doesn't really point to anything at all. It doesn't point to any particular valid area of memory. And we'll come back to pointers later. In C++, the various entities in your program, and by entities I mean things such as types or objects, in other words variables in your program, or functions, and various other things, all of them have to be named by an identifier. And in order to be able to use that identifier, you first have to declare it. So a declaration in the language, it introduces an identifier. In other words, it introduces a name that you plan to use for something, and it gives some very limited information about that identifier that you're introducing. And in C++, you have to declare an identifier before you use it for the first time, unlike some programming languages where you can just introduce identifiers on the fly. Another term I need to introduce is the notion of a definition. A definition is similar to a declaration. It sort of includes a declaration as a subset in some sense, but it provides full information about the identifier that you're trying to introduce. And I'll come back to a little bit more specific details about declarations as definitions as we go through some of the subsequent slides. Really, for the time being, I want to focus mainly on declarations and definitions of objects. And in the case of objects, in other words, variables in your program, declaring an object also typically defines it, although there are some exceptions that we can find in the language. You can declare an identifier multiple times, but you can only define it once. This is one of the rules of the language. And although declaration and definition do mean actually different things, a declaration only gives kind of part of the information about the identifier you're introducing, whereas a definition gives full information about it. In spite of this, people often use these terms interchangeably because it would be just too simple and straightforward if everyone really said what they meant. So just be aware that sometimes people abuse the terminology declaration and definition, but they do actually technically mean different things. On this slide, we have some examples of declarations and definitions of various different entities. Don't get too hung up on the details of this slide because there's some things here that we haven't really talked about yet, and we'll come back to them in more detail later. Really what I want to focus mainly on this slide is declarations and definitions of objects, in other words, variables in your program. So if we look at the top of the slide, for example, this is an example of a declaration and a definition of the identifier count. This is basically causes a variable to be declared that's called count, and the type of this variable is int, so it's an int of integer type. This is both a declaration and a definition. It's a declaration because it actually tells the compiler that count is an identifier, and this identifier count is associated with type int. It's a definition because in addition to doing what a declaration does, it also causes memory to be allocated to hold the value of this variable called count, and actually causes it to be created in your program. So that's the definition part, the actual allocation of storage and the creation of the object. The next line here is an example of a declaration that is not a definition. Here it's declaring an identifier called alpha, and specifically it's declaring an object or variable in your program called alpha. The type of this object is double, so it's basically a floating point type quantity. And the extern keyword here, which we'll talk about a little bit later, it just says that this variable is actually defined somewhere else. So only declared, it's defined in some other part of the program. The other examples here relate to declarations and definitions of functions and types, and we'll come back and talk about these in more detail later after we talked about functions and types in some detail. In C++, we can create arrays of objects. An array is a collection of one or more objects of the same type that are stored contiguously in memory. By contiguous, I mean that they're stored all in consecutively addressed memory locations. And each element in the array is identified by a unique integer index, and indexes for arrays in C++ start from 0. In some programming languages they use 1, but in C++ everything indexes from 0, just like in C. And arrays are denoted by square brackets. So some examples of arrays would be the array which we're calling X here. It's of type double, and there's 10 doubles in this array. So this would actually allocate storage for 10 doubles in memory. They're all consecutive in memory, and they're indexed from 0 to 9. Here we have an integer array. It's a two-dimensional array, so it's a 512 by 512 array, which is storing ints, in other words integers, and it's called data. And if you want to access elements in the array, use the subscripting operator, which uses square brackets. So for example, if we create an array called X, which is an array of 10 integers, 10 ints, the elements of the array, if we want to access the very first element in the array, it's indexed or accessed by X with 0 in square brackets after it. So this accesses the 0th element in the array, which is the first one. This accesses the second element in the array, which has index 1, and so on up to the 10th element in the array, which has index 9. All this said, though, in C++, you rarely ever need to use arrays. More typically, what you'll use is either the array type in the standard library, or the vector type, or some other, similar sorts of types. And we'll come back and we'll look at the array and vector types later. Again, arrays are not used that frequently in C++ because there's a number of advantages to using things like the array type and vector type and so on. But we'll come back to this later. This slide shows a more detailed example involving an array to give you a more concrete idea about how arrays are laid out in memory, and so you can contrast them with some of the other concepts that I'm going to be introducing shortly. So in this example, we're creating an array called A. It's an array of 4 ints, so 4 integers. And we're also on this line of code initializing the contents of this array to have the elements 1, 2, 3, 4. So the first element in the array has the value 1, the second element has the value 2, the third has value 3, and the fourth has value 4. And for the purpose of this example, I'm going to assume that the amount of bytes in memory that are required to store a single int is 4. And for the sake of this example, I'm going to assume that the array A is stored starting at memory location 1000. In other words, it's stored starting at address 1000 in memory. So the picture that, in terms of how this array would be laid out in memory, looks like what's shown down below here. So we're saying, just for argument's sake, hypothetically, suppose the array starts at memory location 1000, then the first element in the array, which has index 0, so A0 element, is going to be stored first. And we said suppose it has the value 1 up above here, it's initialized to 1. So the value 1 is stored in this location. And because we're saying suppose that each int requires 4 bytes in memory, if the first int starts at memory location 1000 and each one requires 4 bytes, this means the second integer in the array will start at memory location 1000 plus 4, which is equal to 1004. So this is the second element in the array, and it would be accessed by saying A with the subscripting operator with the value of 1 plugged in for the index here, and so on. So this is a sort of picture that we have with arrays. The key thing to note here is that the array is laid out contiguously in memory. So all of the memory locations that are used by the array are consecutive in memory. There's no gaps or spaces in between elements in the array. The next concept that I need to introduce is the notion of a pointer. A pointer is an object whose value is the address in memory where another object is stored. And in the language, pointers are denoted by a star. So for example, if we have an object of type t, so for example, maybe t corresponds to int, if we want to denote pointer to int, we would say int star. In other words, we just put a star after the type name, and it changes the type from the original type t into a pointer to type t. And in the language, there's something called a null pointer. A null pointer is a special pointer value that's guaranteed never to point to any valid data. And in particular, there's a key word in the language, which was briefly talked about earlier, called null putter. And this keyword corresponds to that special value for a pointer, which corresponds to a place in memory where no valid data is ever placed. So in other words, null putter can be used as a special value for a pointer to say that it doesn't really point anywhere. It doesn't point to any valid data. In order to access what a pointer points to, in other words, a pointer by definition of what it is, it refers to or references some other place in memory, because the value of a pointer variable is the address in memory where another variable is stored. So sometimes we want to actually look at the value that's stored in the pointer variable and then go to where that pointer variable is referring in memory and access what's there. And this process is called dereferencing. So to make this a little bit more concrete, if, for example, we have a pointer variable called p, and then we want to access the actual data that that pointer refers to or points to, we would say star p. So putting star in front of a pointer dereferences. In other words, it goes to whatever that pointer is referring to and accesses what's there. Sometimes we may have a variable or object, for example, called x, and we may want to know where is it stored in memory. And there's what's called the address of operator in the C++ language, which is denoted by this ampersand character here. If we have a variable x and we put an ampersand in front of it, this gives us the address in memory where that object is stored. So if we have a variable and we want to get a pointer to it, in other words, we want to find out where it's stored in memory, we can put an ampersand in front of it. So as an example here, just to finish off this slide, suppose we have a character, a char variable called c. So c is basically holding a single character. And then what we do next on the next line here is we create a pointer to a character, a variable that holds a pointer to a character. If we had just char here, it would be just a variable of type char. But because we put the star here, it means pointer to this type. So this means pointer to char. So it's a pointer to a character variable. So we initialize this pointer variable, for example, with the null putter literal, which just means initialize the pointer essentially to point to nothing, because null putter is a special pointer value which never refers to any valid data. So we might want to initialize our pointer this way just so that we know it's not really pointing anywhere to any specific data. Or we might do something like on the next line here, where we create a pointer variable called cp2. Its type is a pointer to char. In case it's helpful, the type names sort of read from right to left. The star means pointer, and then char. So it's a pointer to a character, a pointer to a char. In this case, instead of initializing it to a null putter, what we do is we initialize it to point to the variable c. Because up above here we have a char variable called c, and here we're taking the address of c. So address of c corresponds to a pointer which points to c, and then we're initializing this pointer value cp2 by assigning to it the address of c. So cp2 will then hold as its value the address in memory where c is stored. On this slide I have an example to better illustrate the concept of a pointer. So at the top of the slide we have a little code snippet, 3 lines of code here, C++ code. And initially what we do, we create a variable I of type int, and we initialize it to 42. Then we create a variable called p, which is a pointer to int. It's a pointer because of the star here. Star means pointer. And we initialize it to the address of I, in other words, the place in memory where I is actually stored. And then we just check to make sure that if we dereference the pointer, that the value that we read from dereferencing the pointer is 42. In other words, the value stored in memory where the pointer points is equal to 42. So that's our code snippet. And for the purposes of this example, I'm going to make some assumptions, which is the next bunch of information on the slide here. I'm going to assume that variables of type int require 4 bytes in memory, and that pointers to int require 4 bytes in memory. This is hypothetical and fairly arbitrary. There's certainly some architectures for which this will be true, but there's some for which this won't be true. Again, but this is just hypothetical for illustrative purposes. I'm going to assume that the variable I is stored in memory starting at memory location 1000, and I'm going to assume that the variable P is stored in memory starting at the memory location 1004. So you have a picture that looks like this. At memory location 1000, we have the variable I stored in memory, and at memory location 1004, we have the variable P stored in memory. So when the code starts executing, when we assign 42 the value of I, this is going to place 42 into this area of memory here, because this area of memory corresponds to the variable I. On the next line, when we create this variable P, this pointer variable, we initialize it to the address of I. So the address of I is the place in memory, the address in memory where I is stored. So if we look at our memory layout down below here, you can see that the variable I is stored in memory starting at memory location 1000. So the value that we get when we take the address of I, the value address of I is going to be 1000, because 1000 is where I is stored. So the value of 1000 will be assigned to the pointer P. So you can see down below here, we've stored the value 1000 into P. Now on this last line of our code snippet here, where we're saying star P equal 42, what this is doing is it's checking to see, is the value that is stored in where the pointer P points to equal to 42. So we're dereferencing, putting this another way, we're dereferencing the pointer P. In other words, we're going to where the pointer points, accessing what's there, and then checking to see if this is equal to 42. So if we look down below here at our memory picture that we have, when we say star P, what this does is we go to where P is stored in memory, which is memory location 1004, which has the value 1000. And when we say star P, what this does is it reads the value of the pointer P, which has the value 1000, and then it goes to memory location 1000. In other words, it goes to where the pointer points and accesses what's there. So star P means go to where the pointer points and access whatever it's pointing to. So because the pointer P is pointing to memory location 1000, when we say star P, this will access whatever is at memory location 1000, which is the value of I, which is 42. So the value that will be read for star P, in other words, star P will have the value of 42. So this comparison is true. Star P has the value 42, so therefore it will compare equal to 42. And this is basically the complete example. So hopefully that helps to clarify in more concrete terms what exactly a pointer is. The next concept I need to introduce is that of a reference. A reference is essentially an alias or nickname for an already existing object. And in the language, there are two different kinds of references, what's called an L-value reference and what's called an R-value reference. And I won't go into detail about historically where the term L-value and R-value come from. It will probably only confuse you and not really serve to help you have a better understanding of references, because the reason these terms were used originally no longer apply anymore in the language. So it's probably better if you don't know what L-value and R-value stand for. L-value references are denoted by a single ampersand character. So for example, if we have an object of type T, so for example maybe T is int, and then we put an ampersand after it, so we say int ampersand, this would correspond to an L-value reference to int. So a reference is a type of type, a kind of type in the language. There's also what we call R-value references, as I mentioned, and R-value references are denoted by a double ampersand. So if you have some type name, like maybe T is int, for example, and then you put a double ampersand after it, so you have int and then ampersand ampersand, this would be an R-value reference to int. And a little bit more terminology, when we create a reference, we also have to initialize it to refer to something, and this process is called reference binding. In other words, when we initialize a reference, the act of initializing the reference is called binding the reference, or reference binding. And without getting into a lot of details, it's hard to explain kind of very precisely the difference between L-value and R-value references. They both are references in the sense that they're an alias or nickname for an already existing object. The main difference is sort of functionally how they behave in the language, how you're allowed to use them, and so on. For the purposes of most of what you're likely to be doing in your programming, in most contexts, it's usually L-value references that you want to use. The only place where you probably would want to use what are called R-value references is in the context of things called move constructors and move assignment operators, or if you're doing more advanced programming, there's lots of other places where you might use R-value references, but in kind of more straightforward programming, typically the places where they arise are these things called move constructors and move assignment operators, which we'll discuss in much more detail later. And I can't really discuss them in any sort of meaningful way at this point because it requires a much deeper understanding of the language. But we'll come back to this much later in much more detail. But just to give some examples, I have a variable x which has type int, and then what I do is I create a reference to this variable x. So I create a reference to int. Remember, the type names often it's kind of helpful to read them from right to left. So we have this ampersand here, which means reference, and then we have int. So it's a reference to int, and this reference variable, we're calling it y. And again, in terms of terminology, when we initialize this reference y, the process of initializing it, when we're initializing it to x, this is called reference binding. So here we're binding the reference y to the object x. And essentially what this does is it makes y a nickname for x. It doesn't actually create a new variable y. Y and x are the same variable. It just says y is another name for x. It's just a way to create a nickname for a variable. It doesn't actually create a new variable. And then, and this is an L value reference because we have a single ampersand here. On the next line we have int followed by 2 ampersands. So this particular identifier TMP, it refers to an R value reference to int. Again, it's helpful to read these type names sort of right to left. It's double ampersand, so it's an R value reference, and it's an R value reference to an int. And in this particular case, this R value reference is referring to 3. So temp is just a nickname for the value 3. To better illustrate the concept of a reference, I have an example on this slide. And at the top we have a small little code snippet, a few lines of C++ code. And what we're doing here is we're creating a variable called I, which is type int, and we're initializing it to 42. Then we're creating another identifier here called j, which is a reference to an int. So j is going to be essentially a nickname or alias for another int variable. In this case, it's going to be a nickname or alias for the variable I, because when we're doing the initialization of this reference j, we're initializing it to I, or in terms of more formal terminology, we're binding j, the reference j, to the object I. And then on the last line here, we're just checking to make sure j is equal to 42. In terms of this example, I'm going to make a few assumptions just so that I can draw a more concrete picture with specific numbers on it. I'm going to assume that ints, the int type, requires 4 bytes of storage in memory, and I'm going to assume that the address of I, this variable up here, I'm going to assume that I is stored in memory starting at memory location 1000. These assumptions are very arbitrary and hypothetical, but it's necessary just to be able to make a more concrete picture below of how things are laid out in memory. So if we look at the code snippet that we have up above, the first thing that we do is we create an integer variable called I, and we initialize it to 42. So in terms of memory, what this is going to do, we said suppose that I is allocated memory starting at memory location 1000, and it takes 4 bytes of memory. So we have 4 bytes of memory here, and we're going to stick the value of 42 into this memory because we're initializing I up above to 42. And then this particular memory location 1000 here is going to be associated with the name I. So if we say I in our code, it's going to be referring to this variable here that has the value 42. Then on the next line here, we create a reference j. It's a reference because we have this ampersand here, so it's a reference to an int, and this reference is bound to I. In other words, initialized to I. This does not actually create any new storage in memory. All this does is it says this already existing variable in memory called I, that's sitting at memory location 1000, let's give it another name. Let's call it j also. So now the names I and j both refer to this same variable in memory, the same object in memory. So if I read the value of I, or read the value of j, or write the value of I, or write the value of j, it makes no difference because I and j are actually the same variable. They're just different names for the same underlying object. On this slide I have an example that deals with addresses, pointers, and references, and mainly what I'm trying to do in this example is to help illustrate or contrast the difference between pointers and references, for example, and regular variables. So in this case, or in this example, I'm going to make a few assumptions. I'm going to assume that the number of bytes required to store an int variable is 4, and the number of bytes required to store a pointer to an int is 4 as well. Again, these are just hypothetical for the purposes of this example. There's nothing in the world that says that they have to be 4. What I have on this slide essentially are 3 different examples, one in this left column, and then one in this middle column here, and then one on the column on the right. And basically they each have some kind of snippet of code associated with them, like this code in the left, this code in the middle here, and this code on the right. And then below we have a figure which is describing how things are laid out in memory with the different variables in the example. So for the left case, the middle case, and then the right case. So I'd like to go through each of these and kind of highlight or contrast the differences between them. So in the first case, we have a variable called I, which is of type int, that's initialized to 0. So when the compiler sees the integer new variable I, it has to create space to store it in memory. So for argument's sake, let's suppose that the compiler starts allocating memory at memory location 100. So it's going to stick this new variable I at memory location 100, and it's initialized to 0, so it's going to write the value of 0 into this variable. Then we go on to the next line here. We create a new variable called j. It's of type int, and it's initialized to 1. So what's going to happen? The compiler then allocates another chunk of memory, starting right after the previous variable I at memory location 104, to hold the value of the variable j, which is the new variable that's being created here. And j is initialized to 1, so we're initializing a value of 1 here. Then we create a third integer variable called k, which is initialized to 2. And the process kind of repeats here. We create a new variable starting at memory location 108, just after the previous variable that we created. It's associated with the variable identifier k, and we put the value of 2 into it. Now, if we said, what happens, is there any difference between the line of code which says set I equal to 3 and j equal to 3? So for example, after this line of code here that says int k equal to 2 semicolon, if we stick another line of code below which says I equal to 3, or alternatively add a line of code j equal to 3, is there any difference between these? Well, yes, there is a very big difference. I equal to 3, because I is associated with this memory at location 100, in particular this value in here. This would set the value of this area of memory to 3. Whereas on the other hand, if I set j equal to 3 in this example, j, the symbol j or identifier j refers to a completely different piece of memory from I. It's referring to the memory location at 104. And it would be modifying, if you set j equal to 3, it would modify this value here and set it equal to 3. So this is the first example. Now let's go on to the second example in the middle column. In this case, we have a reference. This is what's making this difference. So the code starts out in a similar way. We create an integer variable called I. It's of type int. We initialize it to 0, so the compiler is going to allocate some memory, for example, say hypothetically at memory location 100, to store the variable I, and it's initialized to 0, so we stick the value of 0 in here. Then on the next line, we proceed to create a reference to an integer. This is my funny way of writing an ampersand in my handwriting. So this is ampersand int. So it's a reference to int, an L value reference to int. So j is an L value reference to int. This reference is bound to I. In other words, j is a nickname or alias for the variable I. This line of code actually won't cause any new memory to be allocated, because all it does is it just says that j is a nickname for I. So j and I both refer to the same chunk of memory, which is the chunk of memory at address 100, which holds this integer variable that currently has the value of 0. So a reference doesn't create any new storage. This is critical to understand. All it's doing is creating another name, j, by which we can refer to some chunk of memory that already exists. This chunk of memory at memory location 100 is associated with the variable I initially. After we create the reference j, j and I both refer to this chunk of memory at address 100. Then we proceed into the third line of the code up above here, int k equal to 1. So k is an integer variable. It's going to, and it's initialized to 1. Since k is a new integer variable, it has to allocate storage for k. So it allocates some storage at memory location 104, for example. It becomes associated with this variable k, this identifier k, and we initialize its value to 1. In this case, if we now consider, is there any difference, if below this last line of code that we have here, int k equal to 1, if we then add either this line of code, I equal to 3, or this line of code, j equal to 3, is there any difference whether we add one line or the other? In other words, is there any difference between I equal to 3 and j equal to 3? In this case, unlike the example in the left column, there is no difference because I and j both refer to the same chunk of memory. It's this integer variable that's stored at memory location 100. So if I set I equal to 3, it's the same as if I set j equal to 3 because I and j are both the same chunk of memory here. So this is what a reference allows you to accomplish. We essentially have a nickname j by which we can refer to the object that's stored at memory location 100, or we can alternatively refer to it by the name I. So references just give us a new way to refer to something that already exists, a new identifier name by which we can refer to something that already exists. Then we move on to the last column, the rightmost column here. And in this case, we have a pointer thrown into the mix. So the code starts out in a similar way. We have int I equal to 0. So we create an integer variable I, and we initialize it to 0. So again, going down below at the memory layout that we have, at address 100, we allocate space for an integer, which is the variable I, and we initialize it to 0. Then we proceed on to the next line of code. This is going to create a pointer to an int, a variable called j, whose type is pointer to an int. So j holds a pointer to an int, in other words, the address in memory where some integer is stored. And we're initializing it to the address of I. So the first thing we have to do is we have to actually create storage for the new variable j that's being created. So we said suppose pointers are 4 bytes, pointers to integers are 4 bytes. So it's going to allocate 4 bytes starting, for example, at memory location 104. So we have our 4 bytes allocated here, and this value of j, the symbol j, which is associated with this chunk of memory at address 104, it has to be initialized, j is being initialized to the address of I. So what is the address of I? Address of I is where I is stored in memory. So we look down below here, I here is stored at memory location 100. So the address of I is 100. So we're going to take the address of I, which is 100, and assign it to j. So j is now going to have 100 stored into it. Now if we look at these two lines of code below here, suppose that after this last line of code, int star j equals %I, suppose that we add below this either I equal to 3 or star j equal to 3. Is there any difference between these two lines of code? In other words, if we add this line below this last line here, or we add this other line, star j equal to 3, below this last line up above here, the answer is there's no difference. I mean, functionally, they will achieve the same thing. They'll both end up setting the variable I to 3. If we execute this line of code, it kind of in a very direct way sets I equal to 3, because it just says, take whatever memory is associated with the symbol I, and the symbol I is associated with this chunk of memory here, and it sets it to 3. So this value of 0 would be changed to 3. On the other hand, if we instead executed this line of code, star j equal to 3, this would accomplish functionally exactly the same thing, but doing it in a sort of indirect manner. What we would do is we're essentially dereferencing, because star, if you put star in front of a pointer, it dereferences the pointer. In other words, it goes to where the pointer is pointing and accesses what's there. So in this particular case, we say star j. Well, what does that mean? That means we read the value of the pointer j, so we read the value of 100, and then we go to where this pointer points. This pointer is pointing to memory location 100. So we go to memory location 100 and we access what's there. Well, what's there is the value of the variable I. So star j is essentially giving us the value of I. So if we say star j, and star j basically is referencing I, and then we say star j equals 3, this is going to have the effect of setting I equal to 3. So both of these lines of code would be functionally equivalent. The only difference is this one is maybe a little bit less efficient because we first have to read the value of the pointer and then go to where it's pointing, whereas this way we're just directly modifying I. But functionally they achieve the same thing. They both set I equal to 3. Sometimes in C++ code it's convenient to be able to create an alias or nickname for an existing type. And one way to accomplish this is using the typedef keyword. And just to give an example, suppose we have a type long, and we want to create a nickname for this type. We want to refer to it by another name, for example, called big int. So we want big int to be a nickname for the type long. So anywhere we say big int, it's the same thing as if we said long. This can be accomplished with this typedef keyword. So the kind of pattern here is we say typedef, and then the name of the already existing type, which in this case is long, and then the name of the new type that we want to be a nickname for this already existing type. So the new type is big int. So then, for example, on the next line, if we say big int I, this is exactly identical to saying long I. So big int is just a synonym for long. And this is useful for, this sort of type aliasing is useful for a number of reasons. Sometimes it can make the code more readable because we can choose this name, this nickname, to be something which has a very well-defined meaning associated with it. In other cases, it can be useful to use type aliases because sometimes the type names in C++ can get quite long. And sometimes in order to achieve a shorter type name, you might want to create a type alias like this. In C++, there's a second way in which we can create type aliases. So far, we've talked about the typedef statement. Another way we can achieve a similar effect is with what's called a using statement. Basically, this keyword using, which appears in the language. And for reasons that I won't get into here, it's probably preferable to use a using statement rather than a typedef statement. The using statement wasn't in the original C++ 98 standard. It was later added. Typedef has been there since the beginning of time. It was inherited from the C language, but the using statement is something new, and it was introduced because it has certain advantages over typedef. There's some things that you can do with the using statement that you can't do with a typedef. And for this reason, it's probably preferable to use a using statement over typedef, just for consistency. But anyways, just to give an example, suppose that in our code we have a type name called bigint, and we want it to be an alias or nickname for the type long. This is similar to what we had on our previous slide involving the typedef statement. Then we would use a using statement which has the form that's shown here. So we say using, and then the identifier, which is going to name the type alias that we're trying to create, and then an equal sign, and then whatever existing type that our new type alias is supposed to be a nickname for. So this would make bigint essentially a nickname for long. And then we could write code, for example, we could say bigint I, and this is the same as saying long I. It's going to create a variable called I, which has type bigint, which is type long. So again, whether you use typedef or using, to some degree it's a matter of preference. There are some situations in which you'll have to use a using statement because you can't achieve what you want to achieve by using typedef. As a matter of consistency, though, I would probably recommend just always using a using statement. Sometimes the need arises to declare an object or function that's defined in a separate source code file, a separate C++ source code file, without actually defining it, because of the fact that it's actually defined in some other file. And for this purpose, there's a keyword in C++ called extern, and this serves the purpose of essentially saying that some object or function is defined elsewhere. You want to declare it here, but don't also define it. Just only declare it. So for example, maybe we have a global variable called evil global variable, which is of type int, and we want to use it in this file, this source code file that we're looking at now. In order to use it, you have to first declare it, right? Because in C++, you have to declare every identifier before you use it. So we have to declare it, but we don't want to declare it and define it because we know it's defined in some other source code file. So what we would do is we would put the extern keyword in front of int evil global variable. And by putting extern here, what this does is says, I'm only declaring this variable. The actual variable is defined elsewhere. In other words, the actual memory that's allocated for the variable is done in a separate source code file. So occasionally you may need to use the extern keyword. And remember, you can never have multiple definitions of a variable in C++. So this is the reason why it's important to not define the variable a second time if it's already defined in another file. The next thing I want to look at is the const qualifier. The const qualifier is something that can be applied to a type to specify that that object has a value that's constant. So the const qualifier is expressing the notion that something's not allowed to be changed. For example, suppose that we want to define a variable called x, which is of type int, but we want to make sure that this variable can't be changed. So when we create this variable x of type int, we initialize it to 42, and we want to make sure that it never changes. The value 42 can never be changed, so what we do is we put const in front of int x. So essentially what this does is says that this object x cannot change. This code is not allowed to change the value of x. And just to kind of further illustrate the notion of the const qualifier, I have some example code down below here. So let's look at this code. So we're first creating this variable x. It's of type int, and we've qualified the type by const. Const is actually part of the type. It's basically an integer that can't be modified if it's const int. So const is actually part of the type. And we've initialized it to 42. So it's initialized to 42, and then because it's const, we can't change its value. So not surprisingly, the next line of code would actually generate a compile error if we tried to compile this code, because the compiler is going to say, what are you doing here? You're trying to assign to x some value, but you said that x is constant. You're not allowed to change it. So you're not allowed to do this, compile error. So the compile error will occur. The next line here, we create a reference to our variable x. So we're going to create a reference to integer, and specifically it's a reference to an integer that's constant. Again, type names, it's helpful maybe to think of, at least for simple type names, if you're reading them from right to left. So we have ampersand, int, const. It's a reference to an integer that's constant. So we bind this reference x1 to x, and this is okay. This won't generate any kind of compile error. It's a valid thing to do. After this line of code executes, x1 just becomes a nickname or alias for x. If I say x1 in my code, it's the same as if I said x, because they both name the same chunk of memory. Then the next line, we're dealing with a pointer in this case. We have a star here, so we're creating a variable called p1, and it's a pointer to an integer that's constant. So the pointer itself is not constant. I can change where it points to, but the thing that it points to is constant. So this const here refers to the thing that the pointer is pointing to. And we're initializing it to the address of x. So this pointer p1 is going to be pointing to x. And this will not cause any compile errors. This will work fine. The next two lines are the interesting lines, because they actually won't compile, and they won't compile for reasons that might not at first be completely obvious. But if you stop to think about them a little bit more, it becomes more apparent why these things are not valid to do. So on the next line here, there's this line involving the variable or identifier x2. What we do in this case is we're creating a reference to int. Again, ampersand is a reference, so it's an L value reference to int called x2, and we're trying to bind this reference to x. In other words, again, bind just means initialize. We're trying to initialize this reference to x. So that means that after this line of code executes, x2 just becomes a nickname or alias for x. So down below we could say x or we could say x2. It would make no difference because they both refer to the same thing. However, this line of code will not compile, and it's really critically important to understand why, what the problem is, because this sort of problem is something that newcomers to C++ often have a great deal of difficulty with at first. And the issue here is the const qualifier. If we look at what we have more carefully, remember x was defined up above to be const int x. So it's a constant integer. It's an integer that cannot be changed. And the language takes the word const very seriously. If you say something's const, in other words, if you say it shouldn't be changed, the compiler is going to make sure that it isn't going to get changed. And it's not going to let you do anything directly or indirectly. And this is the key thing. It will do everything in its power to make sure that you do not create some sleazy backdoor way that indirectly you can change something that's const, something that's supposed to never be changeable. So if we look at this line of code again, now I can try to explain the reason why it's not valid, why it will fail to compile. It will generate a compile error. The reason why is we're trying to create a reference to an integer. Notice that this is not a reference to an integer that's constant. There's no const in front of the int ampersand. It's just int ampersand, meaning this reference is a reference to an integer, and we are allowed to change this reference, the thing it refers to, because there's no const here. So that means we're allowed to change x2. It's perfectly legitimate to change x2. However, x on the right-hand side here, if we look up above here, x is constant. X cannot change because we've said that it's const, so it's not allowed to be changed. Now, if the compiler let this line of code compile, because x2 is just a nickname for x, x2 and x are the same thing. They refer to the same chunk of memory, the same integer in memory. So if we're allowed to change x2, we can basically assign values to x2 and change its value. But the problem is x isn't allowed to be changed. So if the compiler let this compile, it would give us a sneaky backdoor way that we could change the value of x, because what we could do is we can change x2, and we're allowed to change x2 because x2 is a reference to an int, not a reference to an int that's constant. In other words, it's not const int ampersand, it's just int ampersand. So we're allowed to change x2, but x2 is a reference to x. In other words, x2 is a nickname for x, but x isn't allowed to be changed. So if this line of code compiled, we could change the value of x2, which would also change the value of x, because x2 and x are the same thing, because one is a reference to the other. But we're not allowed to change x because x is constant. So what the compiler does is it says this line of code is invalid. It will not compile, because if it did compile, you would now have a backdoor way to change the value of x, which is supposed to be constant. If we move on to the next line here, we have a similar sort of problem, but for a little bit of a different reason. In this case, we have a pointer variable called p2, and p2 is a pointer to an int. And the key distinction to make here, it's a pointer to an int, not a pointer to an integer that's constant. In other words, there is no const out front here in front of the int star. There's no const where the mouse is pointing here. Because of this, we're allowed to change the thing that this pointer points to, because the thing that it's pointing to is not constant, so we can change what it points to. So now we're trying to initialize this pointer variable to the address of x. So if this line of code compiled, which it won't, but if it did, what it would do is it would have the effect of having p2 point to x. And if this happened, then what we could do is we could say star p2 equals something and initialize what the pointer points to. However, the thing the pointer points to is x. So if we change the thing the pointer points to, we've just changed the value of x. But we're not supposed to be able to change the value of x because x is a constant variable. It's defined as being const. So the compiler won't let this compile either, because essentially the error here is the thing on the right-hand side is a pointer to something that's not allowed to be changed, a pointer to something that's const. And the thing on the left-hand side is a pointer to something that is allowed to be changed. In other words, a pointer to something that's not const. And you cannot assign a pointer to something that is const to a pointer to something that's not const, because this would give you a backdoor way. By using this pointer here, you could then change the thing that's const. In other words, the thing over here, the x. So this is not allowed either. And although this may seem like a very simple thing, perhaps, this notion of constantness, it's something that causes no end of grief to beginner programmers with C++, at least in my experience anyway. It causes a lot of problems with a lot of students. So try to make sure very clearly that you understand what exactly const means, and more importantly, kind of the indirect effects that it has with respect to, for example, these last two lines of code here. Const is taken very seriously by the compiler, and it's not just that it won't allow you directly to change something as const, but it will try to prevent you from creating any indirect ways that you could change something that's const, which is what makes these last two lines of code here invalid and fail to compile. Earlier we discussed the const qualifier, which is a qualifier that can be applied to a type in order to express the notion of constantness or immutability. In C++, another qualifier that can be applied to types is the volatile qualifier. And the volatile qualifier is used to indicate that the value of an object can change due to an agent external to the program. In other words, if an object is of some volatile type, the value of the object can just spontaneously change without ever being modified by the program. Now the volatile qualifier has some important implications for compiler optimization. For example, in the case of a volatile object, if the value of the object is read multiple times without an intervening write, it's not safe to assume that all of the read operations will produce the same value. So for reasons like this, the compiler is not permitted to optimize away read and write operations on volatile objects. At first, it might seem very strange to have an object whose value can just spontaneously change without the program's intervention, but there are some situations where this type of behavior makes sense. And on the slide, I've identified two of these typical usages of the volatile qualifier. One of them is when the object involved is associated with the register of a memory map device. In other words, the object that you have doesn't really correspond to real memory. It actually corresponds to a register in some hardware device, maybe a timer or a disk device. And because of this, the value of that object can just spontaneously change because the hardware, it corresponds to a hardware register, and the hardware itself may change the value of that register independent of what your program is doing. Another example where the volatile qualifier is often used is for variables that are changed in signal handlers. And I won't get into signal handlers here, but for those of you who might happen to be familiar with signal handlers, this is another typical use of the volatile qualifier. And then to finish off the slide, I have a couple of examples. So I have a variable x, which is of type int, and I want to indicate that it's volatile. So I can add the volatile keyword or qualifier to the type. And then here I have another volatile example of using volatile. I have a pointer to an unsigned char called device status. And maybe this corresponds to a pointer to an area in memory that corresponds to some register in a device. And because it's a register in a device and that the hardware device may actually change the value independently of my program, I've indicated that the value that the pointer points to is volatile, meaning that its value may change just spontaneously and independently from the program. Another keyword in the C++ programming language is the auto keyword. And in various contexts in the language, the auto keyword can be used as a placeholder for type. And in most of these contexts, the implication is that the compiler has to deduce the type. So just to give some simple examples of the use of the auto keyword, we're trying to define a variable called I, and we're initializing it to the value of 3. And notice instead of specifying an actual explicit type for the variable I, we've specified auto. And what this means is the compiler essentially has to deduce the type. And the way that it deduces the type is it looks at what's on the right-hand side of the equal sign, the thing that we're assigning to I, and based on that type of the thing on the right-hand side of the equal sign, it deduces the type of the variable that we're actually trying to define here. So in this case, the variable, or the entity on the right-hand side of the equal sign is an integer literal, and specifically it's an integer literal of type int. Therefore, the variable I will be deduced to have type int. In other words, the type of the right-hand side and left-hand side match one another. On the next line here, we're doing a similar sort of thing. We're creating a new variable called j, and we're specifying its type as auto. So again, the compiler looks at what's on the right-hand side of the equal sign, and on previous line, I was defined to be of type int, so I has type int, so j will have type int. You could also add things like ampersands for references and const and other modifiers to the type that's associated with auto. So in this case here, we have a line similar to the previous line where we're creating a new variable k, and we're initializing it by I. I has type int. So the type that's deduced is going to be int and then a reference. So it's a reference to an integer. So k will have type int ampersand, and so on with these other examples. And the auto keyword is very useful in generic programming because when doing generic programming, the types are not always easily determined. So this gives you a way to essentially let the compiler do the hard work of deducing types for you. Also, the auto keyword can be useful for saving typing because sometimes type names in the C++ programming language can become quite long. So by using the auto keyword, it essentially saves you from having to type these long type names. In a lot of cases, the auto keyword can lead to more readable code as long as it's well used. Sometimes if the code is overused, or if the auto keyword is overused, this can lead to very difficult to understand code. So there's a bit of a balance involved in terms of making good choices when to use the auto keyword and when not to.